So previously we talked about the definition of function continuous at a single point. Basically it means the function is connected at that point. So now if function f is continuous everywhere in an interval, then we say the function is continuous in that interval. For example, for the function y equal to x squared, and from the graph we can see that it's connected everywhere in its domain. So we can say that the function y equal to x squared is equal to continuous from negative infinity to infinity. So everywhere from negative infinity to infinity, it's continuous. Right. So in fact, most functions we have learned before are continuous everywhere in their domains. So for example, polynomial functions, x squared, x cubed, like these things. Or rational functions like x squared over maybe x minus 5, polynomial over polynomial. Well, this is continuous everywhere in its domain, but notice that x equal to 5 is not in the domain. That's why it's not continuous at 5, right? So in the domain, it's still continuous everywhere. Or like root functions, square root of x is continuous everywhere in the domain, x greater than or equal to 0. Trig functions like sine x, cosine x, tangent x, they are all continuous in the domain. Inverse trig functions like arc sine x, arc cosine, arc tangent, they are all continuous in the domain. Exponential like e to the x, or 2 to the x, 5 to the x, they are all continuous everywhere. Log functions like natural log of x, it's continuous in the domain, and the domain is x greater than 0. So all these functions are continuous in their domains. Okay? Of course, not in the domain means not continuous. Okay? Then we can prove that if f and g are continuous, then f plus g, f minus g, any constant times f, or f multiply g, f divided by g, they must be continuous at that point. So for example, if f is say sine x, and g is a simple function x squared, then f plus g is sine x plus x squared, must be continuous everywhere. F minus g is sine x minus x squared, is continuous everywhere. A number times f, like 5 times sine x, is continuous everywhere. F times g, so sine x times x squared, is continuous everywhere. Now f over g is a little special. F over g is continuous everywhere except the points that g equal to 0, because now this function is in the denominator, so it's continuous everywhere except x equal to 0. Okay, so at x equal to 0, x squared itself is continuous, but sine x over x squared is not continuous because it's not defined there. Also, we can prove that if g is a continuous function at a and f is continuous at g of a, then their combination of function f circle g or f of g of x is continuous at a. So which means, like for example, if f is sine, g is x squared, because x squared is continuous everywhere, sine is continuous everywhere, so f circle g is actually f of g of x is sine of x squared. This new function is continuous everywhere in the domain. All right. So now we can create many new functions by old continuous functions, and they are all continuous everywhere. Okay. So what's the use of these properties? Because the definition of continuity is the limit is equal to f of a. Right? So if we, on the other hand, if we want to find the limit, and we luckily know that that function is continuous at that point, then the limit is just equal to the function value at a. In other words, if you want to find the limit, you can just substitute a inside, plug it inside, then you will find the limit. Right? For example, if you want to find the limit of square root of x plus 5 plus natural log of x minus 1, we already know that square root function is continuous. X plus 5 is a polynomial, which is a continuous function. Natural log is a continuous function, and x minus 1 is a continuous function. When they combine together, this is a combination of roots and polynomial. this is a combination of natural log and polynomial, then this new function is continuous in its domain. And we luckily find that 4 is in the domain because 4 won't make any trouble when you plug inside, right? So in this case, if you want to find the limit, you just basically plug inside. So it is 4 plus 5 plus natural log of 4 minus 1. You just replace every x by 4. And if you don't have any trouble, then you calculate that. That's square root of 9, that's 3, plus natural log of 3. So that's the answer. So direct substitution property can be extended to any continuous function. Right. So previously we talked about for rational function, polynomial function, it's fine. Now for any continuous function, you can just plug inside if they are in the domain.